Okay. Excellent. All right. So it is a great pleasure for me to introduce the next speaker, Matías Menni from CONICET and Universidad Nacional de La Plata, Argentina. I'm sorry about the pronunciation.
That was perfect.
So please take it away.
Thanks. Thanks for the invitation. I always like the idea of this meetings for Italians. Now, being invited, it's quite an honor. So let me go south for a little bit. You know, Bill O'Veer died recently. And but fortunately, he left us a lot of work to do. What I'm going to talk about today is based on some of his ideas about how to interpret Cantor's work directly, rather than through the work of his editors. Bill says in one of his papers that the word isomorphism has two kinds of meanings. First, in an actual category, some maps in particular might be invertible. And second, an equivalence relation among the objects is defined by the existence of isomorphisms in the first sense. And hold on. While Cantor, of course, used the second abstraction too as same cardinality, he seems to have used the term cardinale to denote a prior, more particular abstraction in which, and here is what I want to emphasize, an actual category of a more purified nature is extracted from a richer one, accompanied by specific connections between the two categories. So, yeah, here I have isolated that last phrase, an actual category extracted from a richer one, and I have drawn a naive picture, trying to think of it as the richer category as a category of spaces, and from there trying to extract a category of discrete spaces or zero-dimensional spaces, something of that sort. And what could be the specific connections between these two categories? And experience suggests at least two connections. First, left adjoint connected components functor, which should have some property so that it behaves like a connected components functor. And here, I'm going to use stable units for a distinguishing property, which implies preservation of finite products. The other specific connection I have in mind is the existence of a colimit preserving right adjoint, which should be thought of as assigning to each space the corresponding discrete or zero-dimensional space of points. Let's look at a classical example to have a glimpse of this intuition in more mathematical terms. Consider the category of topological spaces and continuous maps between them, and in there we can find the totally disconnected spaces, which, remember, these are the spaces that satisfy that the only connected subsets are single points. It is a reflective subcategory. This is classical. The left adjoint sends a space to the totally disconnected space of connected components. This is connected component in the precise definition, in the precise sense given by classical topology, right? And the theorem says that this adjunction has stable units, meaning that the left adjoint preserves pullbacks over totally disconnected spaces. You should know too that it also preserves all products, but never mind that. So in this case, we have extracted a category of sort of discrete topological spaces with a good left adjoint. It preserves many pullbacks, not all of them, but many. Let me give you another example. Now let's consider the category of totally separated spaces. That means that the clopens separate. Again, the subcategory is reflected. And let's now go through the construction. We denote by boldface 2 the discrete topological space with 2 points, and then we have a canonical map to this product, and we can factor it as a regular epi followed by a monomorphism. And that's a reflection, the unit of the reflection into totally separated spaces. In this case, the topological space pi0 is the space of quasi-components, again, in the classical precise sense. Now, in contrast with the case before, this adjunction does not have stable units. Now, intuitively, this sigma here equates 2 points if they have the same clopens around them. For some reason, this intuitive construction of the connected components does not have stable units. Now, let me change the sort of example I have in mind. And now, instead of topological spaces, let's consider a hyperconnected geometric morphism. Recall, this means that the inverse image is full and faithful, and the k-unit of the adjunction is monic. Again, we think of the larger category as a category of spaces, the inverse image as the full subcategory of discrete spaces, the right adjoint as assigning to a space the set of points, and the monic k-unit as the discrete core of the object in question. And here is the construction of a pi0. So if you have one of these hyperconnected geometric morphisms, then the following are equivalent. The discrete spaces form an exponential ideal. That's one of the equivalent conditions. And the second one says that this inclusion has a finite product preserving left adjoint. The interesting part, of course, is that for some reason, being an exponential ideal guarantees the existence of a left adjoint. You can build it. And how do we build it? Well, let 2 denote the subobject classifier in S, and let boldface 2 be the discrete space with the discrete space determined by the subobject classifier in the base. That's an object in E. And now from X, we have the canonical map into its double dual, and then we can restrict the exponent to its discrete part. So we have a canonical map from X into a copower of the discrete space determined by the subobject classifier in the base. So we can factor it as an epi followed by a mono, and the epic part turns out to be the unit of an adjunction, because the fact that well, never mind. Being an exponential ideal implies that the left adjoint preserves finite products. So here I just restated the theorem whose proof I sketched, and let's concentrate on this corollary now. If you have that the base is the category of sets and functions, then the adjunction I just built has stable units. And why is that? This is because every essential geometric morphism over sets is molecular. I mean, this is true, but I hope it bothers you somehow, this statement. Why do we need sets there? And let's compare the 2 constructions. The one for totally separated spaces, which we know doesn't give an adjunction with stable units, and essentially the same construction among toposes, which in some cases does have stable units. Why does stable units fail sometimes for essentially the same construction? Now let me tell you something that looks different at first, but it is quite related. Let's move on to something more general, extensive categories. Extensive categories with products. And recall that an object in such a category is decidable if the diagonal is complemented. So, roughly speaking, this is a discrete space, a decidable object. I invite you to think of it as a discrete space. If you have doubts, you can remember that in the category of topological spaces, an object is decidable if and only if it is discrete. Right? That might give some peace of mind if you've never seen this before. And here's something new. I believe it's new. I looked for it everywhere. I asked people around, and it seems to be new, although it's very, very simple. Let me state it. You have two extensive categories, E and S with finite products. And consider a functor psi from E to S, a finite coproduct preserving functor. Then it preserves finite products if and only if it preserves pullbacks over decidable objects. Right? One direction is trivial. And for the other, assume that the square on the left here is a pullback, whose vertex S is decidable. You know from your first course on category theory that this is the same thing as the square on the right being a pullback. Now, the diagonal on the right is complemented. So because psi preserves finite products and it's a functor between extensive categories, it preserves pullbacks of complemented subobjects. So it preserves the pullback on the right above. And since it also preserves finite products, then the square here on the left below is a pullback. But that just means that the square on the right below is a pullback. Couldn't be easier, right? So again, let's consider an extensive category with finite products. Recall the definition of a decidable object. And now consider the full subcategory of decidable objects in the category E. If it has a finite product preserving left adjoint, then the junction has stable units automatically, just because we are considering the right category of discrete spaces. We are extracting the right thing. So if it has a product preserving left adjoint, then naturally it has stable units. So it follows that if we have a Boolean topos, then every connected essential geometric morphism such that the leftmost adjoint preserves finite products, then the geometric morphism is automatically molecular or locally connected, if you prefer. Sorry, someone entered the waiting room, and I will admit it. There. So I was saying that under, if you have a Boolean topos, then connected essential geometric morphism with a finite product preserving leftmost adjoint, then it is molecular, and the inverse image of the geometric morphism coincides with the full subcategory of decidable objects. It has to be that.
Matthias, don't worry about these notifications. We'll take care of it. We also see them and we can take care of them.
Right. No, the problem in the beginning was that it prevented my computer from carry on working, but now I figured it out. So, sorry, let me try to rephrase that in less precise terms, but in easier terms. If you have a sufficiently good geometric morphism towards a Boolean topos, then it's automatically locally connected. In particular, for those who haven't seen it, a hyperconnected geometric morphism is precohesive if and only if the adjunction extends to a string of adjoints, as displayed there, such that the leftmost adjoint preserves finite products. For example, Johnston provided plentiful of examples in this characterization. Over sets, a geometric morphism is precohesive if and only if it has a connected and locally connected side of definition, such that every object has a point. So connected here applied to sides means that it has a terminal object. So it makes sense then to require that every object has a point. And in this case, this is exactly what you need to guarantee that the geometric morphism is precohesive. But of course, as Lovier already explained, we don't want just sets, right? We want in order to have a good theory of toposes of spaces, we need to let the base space be whatever it wants to be, because sets is not always good enough. Lovier used the example of classical algebraic geometry over a non-algebraically closed field in order to illustrate that last statement. Let me give you another one that Thomas Streicher provided for me. It's a very simple one, and it shows clearly that any topos could serve as a base of a precohesive geometric morphism. In fact, the topos of reflexive graphs in any topos is precohesive over that topo. So let's go back to the sufficient cohesion for local connectedness or molecularity. If you have a Boolean topos and you have a precohesive geometric morphism over it, then the geometric morphism is molecular, and so it has stable units. Moreover, in this case, as I already said, the full subcategory given by the inverse image is the full subcategory of decidable objects, and the rightmost adjoint is the full subcategory of double negation sheets. So again, we see in very strong form this idea that Lovier explained in the beginning. You have a sufficient category of spaces, and out of it, you can extract a category of discrete sets. And since you're extracting the right thing, then it should have good properties with respect to the bigger one. Yeah, that's a drawing illustrating the statement. Now the question remains. You see here, I stated this for a Boolean base. But we could wonder whether any precohesive map is molecular. And the truth is that we don't know. Now, a number of people have tried to answer this question, at least to give evidence for its for a positive answer or for a negative answer. For a negative answer, Hemmeler and Rogers built in 2021 an example of an essential hyperconnected and local geometric morphism that is not locally connected. But it's not an answer to our question because it's not precohesive. The leftmost adjoint in this case does not preserve finite products. Once we had an example, it was easier to produce other ones, and you can find some in my paper from 2022. But before that, Garner and Streicher built now an essential local geometric morphism whose inverse image is an exponential ideal, but fails to be locally connected. Again, it's not quite an answer to our question because, again, it's not precohesive. In fact, it's not hyperconnected. On the other hand, I've just given you a sort of positive evidence for the question. I mean, it has a positive answer if the base is Boolean. Now, let's go back to that idea of sets and why over sets things are automatic. Already in 1980, when molecular maps were introduced, Barr and Paré showed that every essential geometric morphism over sets is molecular. But we are doing elementary topos theory. What do we mean by sets here? And that natural question leads you to ask, what are the toposes such that every essential geometric morphism with codomain, that topos, is molecular? Are there such things? Well, there is sets, if you know what that is. But are there other things? For some time, I looked for them, and my intuition was that such a thing would have to be a topos of very discrete things. So you can imagine my surprise when Jens Hemmeler proved last year that if you have a topological space that is T1, then the topos of sheaves on it satisfies this property. Every essential geometric morphism with sheaves on X as a codomain is molecular. So Booleanness has nothing to do with it. It's a lot more general. So I insist, are precohesive maps molecular? I mean, if any of you happens to know the answer, please let us know. Thanks for coming.
All right, let's first thank the speakers for the very nice talk. So thank you. And we have a couple of minutes for questions. So again, if you have any, raise your hand, open your camera and move around, and we'll try to get to you. All right, well, in the meantime, I kind of have one. So if you could go back to, I think was slide 19.
Let me, slide 19.
Yes, please. Well, really, it's not strictly necessary, but I was just wondering, can you give some more logical intuition to this? I mean, some logical intuition to be molecular as a property in this sense.
Yeah. This means, let's consider first, let me try something first. A geometric morphism whose inverse image preserves exponential. Would that sound logical to you? As logical intuition goes, preserving exponentials, I mean, preserving function spaces.
Yeah, I guess so.
I guess if you're into type theory, it might give a sort of intuition, right?
Mm-hmm.
Well, local connectedness means that, but stable under slicing.
Right.
So if I understand the terminology that type theorists use, this means that inverse images preserve dependent products. Mm-hmm. Does that make sense?
Yep.
Yeah, I find trouble with, for some reason, it doesn't look intuitive enough for me. So I prefer this idea of the left adjoint. Molecular maps always have a leftmost adjoint. You don't see it immediately in the definition, but it is there. And I don't know, for some reason, I find easier to think about preservation of pullbacks than preservation of exponentials, but it's totally subjective. It's my wrong wiring.
All right. No, it was very helpful. Thanks. I love to
Welcome.
think more about this. In the meantime, does anybody have any questions? About
I
this?
have a quick question. In the proof about T1 spaces, can you tell us what's happening? Why is it true in that case?
It's very clever. It's very clever. It's so clever that it needs an alternative proof, so that it deserves an alternative proof, so we can see it from other perspective. Anyway, I'll tell you what the Jens proof is. He observes that a closed geometric morphisms are tidy, and then if you pull back something that is essential, you get that the pullback satisfies the Beck-Chevalier condition. And so, if the domain is molecular, then the original essential geometric morphism is molecular, thanks to the Beck-Chevalier condition. Now, what does it mean to be T1? It means that you can cover it with closed points. And so, that's it. Nice, isn't it? Now, what one would like, really, is to have a propositional statement that holds on every topos of sheaves on this form that would allow you to prove directly over that topos that the precohesive topos over it is molecular. So the proof that Jens used cleverly allows you to reduce it to something over a Boolean base. But it seems that, again, it's a very clever way to overcome an obstacle. It's the obstacle that we don't understand the logic of sheaves over T1 space.
But so is it the case that if I have a topos that is that has a geometric surjection from a Boolean topos, a closed geometric surjection from a Boolean topos, then, which is what happens in sheaves over X in this case, then can we infer the theorem?
No, it's not quite that, okay? First, covering with a strong enough cover from a Boolean topos might end up giving you a Boolean codomain.
Mm-hmm.
This is an observation by Peter Johnstone that I don't think is published. And here, yeah, you would need the fibers to be closed, you see, not the quotient.
But that's why I said that the morphism is closed.
No, if you require the morphism to be closed, it will force your codomain to be Boolean. You need something weaker.
Okay.
You need something weaker to be able to reduce it to, for example, take the canonical Boolean cover of any topo. It's not strong enough to guarantee that the pullbacks satisfy the Beck-Chevalier condition.
Yeah, but that cover is not closed at all.
Certainly not. But if you require it to be too strong, then I repeat, the codomain will be Boolean. So you need something in the middle. And certainly it won't serve for every topos. So it is dependent on the codomain. Yeah. Yeah, I don't know. But you seem to be curious about it. So yeah, please, I encourage you to look at it carefully because it is an interesting problem.
All right. Let's see if there's anybody else from the audience that wants to chip in. All right, if not, we thank the speaker again for a very nice talk and a very good problem. Thank you.